Okay. So what we did in our last class, at first, we tried to connect the Lagrangian theorem and the Eulerian theorem, and we come up with this one, the Reynolds transport theorem. We spent significant amount of time on that because that will be the equation for any conservation theory, like mass conservation, momentum, energy. So we spent time this time so that we don't have to spend time when we will derive the mass conservation or the momentum conservation and the energy conservation. So from this equation, we derive the equation for the mass conservation here. That was the equation at first. And then we did some simplification, like for steady flow, what will be the case? We got this one for the steady flow. And I also told that for this class, we will not do anything about unsteady flow. So basically, this is the equation we want to use all the time, right? Then we worked on that and we finally found this equation, mass flow rate for the steady flow, like mass inlet equals to mass outlet. That is exactly same as what you learned in your environment class, like mass inflow equals to mass outflow. Now we stopped there. We need to do one more simplification. We will do that and then we'll start working on class example 15. Okay. So the next simplification is, here we know that is the like rho VA for the fluid, right? Now, do you think for water or any liquid, the density will be changed at inlet and outlet? What do you think? The density of water at inlet and outlet, do you think that will be different or it will be same? That will be same, right? Like no matter what amount of pressure or temperature I apply, there will be maybe insignificant amount of change, which I don't need to consider all the time. That means for incompressible gas, an incompressible fluid, which is liquid, it's incompressible. That means unable to compress. That means P inflow equals, rho inflow equals to rho outflow. Okay. Now what we can do, I can write down again. Rho AV, rho AV, and this time you can cancel rho because that is same in both end. So finally you can have can you tell me what will be the name of AV? Is there any other name for AV? Say it again. M dot was the mass, like rho AV. So you are dropping the rho. The AV equals to what? There is another type of flow rate we learned. What is that? Q equals to AV, right? The volumetric flow rate. So we can write down summation of Q inflow, summation of Q from the outflow, and that is another form of mass conservation. For steady and incompressible fluid. That should be steady flow. Okay. Now, do you think we can use this equation for any types of fluid or only for a certain type of fluid? This equation? Any? Just for the incompressible one, because this one will not work for the compressible one, because for compressible one, rho is not same for the inflow, and they can be same, but we don't know. We need to check that every time. Okay. Okay. So now we have two simplification. One is for steady flow, one is for steady incompressible fluid. I would recommend every time you start from only from the steady flow. Don't start from this point. Okay. Because I saw in the past you use this equation even for the gas and you get wrong answer. So always start with this one, rho AV, rho AV. Okay. Okay. So are we good up to this point, everyone? Okay. That means the total amount of flow in terms of volume or in terms of mass per unit time should be same all the time, right? That is the mass conservation equation. Good. So let's start working on class example 15. We have two problems, 15A and 15B. 15A should be very, it is not that long, but we need to spend a little bit time on 15B. So let's start working on that. Can anyone read 15A? And I will write down the given values and what values we need to find.
Water flows along a rectangular channel having a width of 0.75 meters. The velocity is 2 meters per second. Determine the volumetric condition.
Thank you very much. So they are saying there is a rectangular channel. That means if I want to draw a 3D of this channel, that is the channel, right? A rectangular, and the width of this one is 0.75 meter and the height is 0.5 meter, right? Okay. And so let's write it down. What are the given values? Area of the channel A, since it's a rectangular area, it will be 0.75 times what? 0.5 meter square. Okay, you'll find that one. The next one is if the velocity is 2 meters per second. Now here we need to work a little bit. This velocity, it's coming from this channel parallel to this channel right here. So what I will write down here, the velocity parallel to the channel is 2 meters per second. And I don't know anything else, so I can write down what we need to find. To find the volumetric discharge Q, which is A times V, right? That's what we need to find out. We'll do that. If you are done, I will move to the next slide. Done, everyone? That V is parallel to the channel, but what was the condition of that V? Like this one, that V needs to perpendicular to the area. If you look at here, it's not perpendicular to the area, so we need to do something. What we can do? We need to take the components, right? Okay, that's what we will do here. Yes. So I will just try to draw this is 20 degree and that is V, and this is the area. So I need to find out the velocity which is perpendicular to that area, right? What is the angle here? Again, it's 20, and I will name that V, maybe the horizontal component. Okay, so V horizontal is V perpendicular to the area, and that will be V cosine 20 degree. What is that? What is the value of that? Say it loudly. 0.8. Okay. So that is 1.88 meter per second, right? Okay. That was the pipe, and that was the velocity. Now we can calculate what was the area? Yeah, did you find out the answer for that? Or I will just write down this one. So for this one, that was meter square, meter per second. So the final one will be meter cube per second. But what will be the answer? .7. Okay. So 0.7 is the answer for the volumetric flow rate. That means 0.7 meter cube per amount of water is flowing through this pipe or this channel per unit second. That is huge amount of water. Okay, so that was easy. The only thing we needed to find out or make sure that the velocity has to be perpendicular to the area, right? Okay. So complete that, and then we can start working on part B, which is from your textbook exercise problem number 54. So let's start working on that. Can anyone read the question? Question number. Okay. Thank you very much. So we have a tank here, and we will consider this tank as our control volume. Okay. That is the, I shouldn't use the arrow sign, you will be confused. Okay, so this one is the control volume, like this dotted line is the control volume here. Now, for this control volume, how many inlets we have? Number of inlets to A and B, right? And how many outlets we have? Okay, so we have one outlet. One, which is C, right? So the question is saying through A and B, some carbon dioxide and nitrogen flows through A and B within that control volume, they get mixed up, and through C, a mixture of those are coming out. So let's write it down. What are the given values? And then we will know what is the unknown we need to find. Okay. So what is the very first thing you know? VA, right? Which is the carbon dioxide, 10 meter per meter per second. What is the next one? VB, which is nitrogen, 6 meter per second. What is the next thing you know? Okay, so pressure A and B, right? Is 300 kilopascal. Now, they didn't say anything, it's absolute or gauge. Since they didn't mention anything, we will consider that as gauge pressure, okay? Because if it was absolute, they would mention that this was the absolute pressure. So I will make a note here that this is the gauge pressure, okay? What else we know? Temperature 250 degrees centigrade. Now from the unit, it's not Rankine, it's not Kelvin. So the pressure is at the temperature is relative or the absolute. Yes, good. Okay, so I'll make that one also. Now the last thing is they give you the mixture of density. That means the density of C, density of mixture, (1.546 kg per meter cube), right? All of these are the given values. Now, after hundreds of given values, what we need to find? What we need to find from these? The velocity at C or the velocity of mixtures, right? So V, C, V, mixture. What is that? I need to find out that. So we are done with first step, that we identified the given values. We identified what we need to find. Now the next step is we need to connect, or we need to find one equation which can connect unknown and known, right? Now from the given values, we have rho, we have density, we have velocity. We kind of know that we need to use the mass conservation equation, right? And They said that the steady rate at sea. So obviously we need to use the steady mass conservation equation. Also, I said we will not use anything unsteady. So we don't need to start from the very beginning. Rather, we will start from the steady mass conservation equation. Okay. So let's start mass conservation equation for steady flow. If I can remember properly, that should be inflow rho AV, outflow rho AV, right? And you told me how many inlets we have here? We have 2 inlets and 1 outlet, okay? So that means, and A and B, those are the inflow or inlets. So what I will write down, rho AV A plus rho AV B, and we have only 1 outlet, rho AV C, right? Now, I think you are in better position than me because all of my given values in the previous slide. So what you can do, identify which values are given and write down in that way, okay? So do you know rho A at this point? You don't know rho A, and you can't use that one also because we have a pressure and temperature. We need to calculate that. So we will work on that. Rather, at first write down what things we already know, okay? So I will just write down rho as it is. Can you calculate the area of the A? Is there any way you can calculate? Pi. Yeah, pi d square over 4 or pi r square, right? And what is the VA? 10. Okay. I don't know anything about rho B also. I will just, and for area here, pi 0.15 over 2. Okay, I should use different type of parentheses here. Okay, I will just change a little bit. What is the velocity for VB? 6. Do we know the density for C? 1.546. We know the diameter here, so pi 0.1 square, and we don't know the velocity there, right? Okay. Are we good up to this point, everyone? Now we need to do 2 more things. We need to calculate rho A and rho B. How to calculate rho A and rho B? You know the temperature, you know the pressure. Ideal gas law, great. We know that there is an equation called ideal gas law. We need to use that. So if for any reason they gave you the rho A and rho B, your life would be so much better, but they didn't give you. So we need to calculate that. So let's calculate rho A and rho B for the temperature and pressure given, okay? So I'm moving to the next slide. Rho A What was the equation for the ideal gas law? P equals to rho RT. So rho equals to P over RT. A is the carbon dioxide. So, and the P is what? 300 kilopascal. And we need to add the atmospheric pressure as well, right? And the atmospheric pressure is what? 101.3 10 to the power. I will just make a note. P atmospheric. Can you give me the R value for the carbon dioxide from the appendix A? And the temperature will be what? 250 plus 273 K. Give me the R value for carbon dioxide. $188.9. Okay, and you got that from appendix A, right? So I will just appendix A, and this whole thing is absolute temperature now, right? Okay. So do the calculation here. What will be the rho with proper unit? While some of you are calculating this one of you can help me with the next part so we can save some time. The pressure was same again. Find out the R value for nitrogen. 296.8. Okay. And everything else will be same, right? $250 plus 273. This time I'm not writing any notes because everything is same. Give me the value for row A and row B with proper unit. Say it again, 4 point. For carbon dioxide, I got a little bit different. That's what I got, 4.06. So I will write down that one. Check your calculation. Okay. 4.62 kilogram per meter cube. What about this one? Rho B or rho nitrogen? Yeah, that's what I got. 2.585. Okay, now we have everything. The only unknown is mixture velocity and the big equation we need to solve. But other than that, rest of the part is easy, right? So what you can do, you can use these two values on this equation here and find out the value for VC. So what I will do, I will move to the next slide if you are done with this one. And I will try to add all the values on that equation, okay? We were enjoying working on that so much that we didn't keep track of our time. I will start from this point on Wednesday, okay? Make sure you bring your class example 15. We will start from this point. Thank you very much.